Okay, so last question of the paper, question 3 part D, says that during the 450-meter fall, the parachuter's gravitational potential energy was reduced by 283,500 joules. So calculate the parachuter's downward speed at 450 meters, which is supposed to be highlighter, assuming that the energy is conserved. Right, now this is a interestingly worded question, and I want to explain how they're wording it first so that you can kind of understand what they're asking. So we know at the top of the fall, say that this is the top of the fall, we know that at the very top that they have a potential energy, and we've calculated this in part A. They had a potential energy of 2,205,000 joules. So at the top there, that's 2.2, megajoules or whatever it is of energy that they have. Then they are falling. And we know that that relationship between the potential energy and the kinetic energy sort of is a sliding scale. So as they fall, they are losing potential energy, but they are gaining kinetic energy. So if they are losing, so if that potential energy was reduced by 283,500 joules, then that has been picked up by kinetic energy. So their kinetic energy is now 283,500 joules because that's been lost by the potential energy, so therefore it's been gained by the kinetic energy. So that's kind of that's the first bit here. So the potential is equal to potential energy lost, basically. All right, so now we know that we're working with kinetic energy. So kinetic energy is equal to half mv squared, where m is mass and v is velocity. And they do want us to calculate that downward speed, which is the velocity at that point. So we know that at 450 meters, if it's only gained that much, it's not at its maximum speed yet potentially, but we do know that it's got that much energy, kinetic energy, so it is moving at a fair rate. Okay, so now we can calculate this. First of all, though, because we're finding V, we need to rearrange this equation. So we have EK, but let's just leave it as EK for the moment. We're going to move around some of these numbers here. First of all, I'm going to multiply by 2. Okay, multiply by 2. Now that's going to cancel out the 2 at the bottom here. So that's going to give me 2EK is equal to mv squared now. Now I'm going to get rid of that, the mass, move it over, divide by m. So that is just essentially, I'm just going to leave it here. So that's going to cancel out the m there. And then we're going to get rid of the square. Opposite of square is a square root. We have to square root everything on the other side. So that's going to cancel out that. And so V now is equal to 2EK on m all square root. Okay. So now we can put in our numbers. So V is equal to the square root of 2 times 283,500. So that's our kinetic energy, divided by mass. And we know that the mass from way at the beginning, so all the way over here, is 63 kilos. So our mass is 63. So we can try and calculate this. Not totally sure if my calculator will do it here, but we'll give it a go. Okay, so we've got 2 times 283,000. 2 times 283,000 is equal to 566, and then divide that by 63 is equal to the square root of, what was that, 8984.12 or something like that. And then let's see if we can square root that. Yep, we can. So velocity is equal to 94.78. 94.78 meters per second, or ms minus 1. All right. Now, that is an excellence question, obviously. If you have sort of found this first relationship here, the first relationship here, EP is equal to EK, that will give you an achieved or got at least the kinetic energy equation right. Merit have some minor errors along the way. For example, haven't done that square root transfer properly, you could get a merit. But the full answer is an excellence question, and you're all capable of doing it. Okay, good luck.